Hello, everyone. Come on in. How's everybody going? Hope you all had a good weekend. All right, got more people coming in. I don't know why. Why is this doing this? My view got changed. There. Oof. All it was bulgy off. Holy crap. There we go. All right, looks like we got about 6 people in the room. It's not quite time for the class to start yet. Anybody have any questions before we get started? You notice that I did open the test, the first test for you guys, even though it's not due for some time. I went ahead and opened it just in case anybody was expecting it, because I suggested I was going to do it this week. So I just wanted to make sure in case anybody wanted to go ahead and start it, that would be the time they could do it. I have to reiterate that when more people get in. We got only 8 of you in here now. So no questions. Hey, Nick, can you talk for me? I want to make sure I can hear you if your speaker works, that is.
Can you hear me?
Yeah, good deal. Thanks, bud. I swear Gerald's in some Caribbean island or something. Makes me jealous. I feel like I'm talking to someone who's telecommuting from Bahamas or something. That makes me mad. I want to be in the Bahamas. All right, got another one. All right, so it's officially class time and time for class to begin, that is. So I just want to reiterate, hey, I made your tests available the end of last week. Let me get Sam in here, probably someone else as well. Now we're up to 10 people in the class. So yeah, as I was saying, I did make test 1 available to you guys. Check the date. I wrote it on there. I want to say I made it till Monday of next week, but I might have made it till Thursday or Friday of this week, but I really think I made it till Monday of next week. So check that, make sure y'all get it done, put it in your calendar on your phone or something like that, so that you won't forget it. You know, missing a test is a big deal. That's a problem.
I'm sorry, when did you say it was due?
I'm pretty sure I made it. It's been since Thursday that I did it, but I'm pretty sure I made it for Monday after this coming weekend, but it might be Thursday or Friday. Just double check yourself to make sure. I just wanted to make sure everybody knew it is open, and it has been open since Thursday of last week. So
Okay, roger that. Thank you.
No problem. Gavin says it's due the 14th, which would be a week from today. Good deal. Thanks, Gavin. I was pretty sure that's what I set it to, but I changed 3 test dates in that same day, and I didn't want to tell y'all something wrong. So yeah, that's on chapters just 21 and 22. You've got some material that's been posted, of course, on my YouTube channel that you can see. There's plenty of Gauss's law problems and line integrals and surface integrals and all that good stuff. So the line
integrals. Is it for 22 and 23? I think you said 2021.
Yeah, we started on chapter 21. I sometimes forget and think we started on 20, but 21 was our first chapter and 22 is our second. So it should be those 2. I always do 2 chapters for each of the online tests.
Okay, I got you.
The next one will be 23 and 24. But remember, all of them will be comprehensive. So next week, you're still going to be doing stuff that you did in chapter 21 and 22, even on the next test. So just keep that in mind. They're all comprehensive. Anybody have any other questions? Course material, tests, questions you run into? I have one student that from my face-to-face class for this class, I had a problem with some capacitor bank problems in the practice test bank. So I got to check that out. I'll let y'all know if I find an error in it. He thinks there's an error. And if it does what he says it does, then it is an error. So I just got to look that up and check and correct it if it is. So we have now finished, of course, chapters 21, 22, 23, and 24. We're going now into chapter 25, which is called electric currents and resistance. So we're starting to look at, instead of electrostatics, which is what we were studying before, electrostatics is the basically the study of charges that are not in motion. And we learned in electrostatics that a conductor is an equal potential surface, and the whole thing's an equal potential surface because the electric field is zero inside of a conductor. And the electric field being zero means the voltage is the same everywhere. But now we're loosening that up. We're no longer studying electrostatics. We're studying basically the ability of charges to move. And the way we do that is we apply electric fields to conductors, and conductors then have an electric field that changes possibly inside of them and compels positive charges to move one way or negative charges the other way. And we're going to use conventional current mostly, which means we're going to pretend that positive charges are leaving the positive terminal of the battery and entering the negative terminal of the battery. Or in AC, it leaves the positive terminal, enters the negative, and then it flips back and leaves the negative, or leaves the positive, which is on the opposite side now, and goes to the negative. But in reality, we'll know that it's really electrons that are doing the moving. And there's only one experiment you can really do, or one type of analysis that you do in which you find out the difference. So you don't have to worry about it. You can just always pretend. But that experiment is called the Hall effect. And basically it combines electric and magnetic fields, and you'll end up seeing if positive charges are moving one way or negative charges are moving that way, you get two different results on the voltage difference from the top of the wire to the bottom of the wire. So in that sense, that's how we figured out ultimately that, yeah, negative charges are moving, not positive. So we're going to pretend, like I said, most of the time that it's just conventional current. That means positive charges are moving. And we're going to start off just by talking about Galvani and Volta. So Galvani was working basically in a lab, working with, in fact, dead frogs and stuff of that sort. And what he noticed was that, electricity applied to the muscles of a frog's leg, for instance, will make it twitch. And later he even noticed that the similar metals touching the leg muscle of a dead frog will make it twitch as well. He thought that might even be basically the essence of the soul. So that was one of the common things we were looking for, the quote unquote life force. And maybe that happened to be the life force that exists even after you're dead or whatever. Not everybody believed that, but it was something they were considering. Volta comes along and thinks maybe it's not that, maybe it's more just the fact that the force or the energy is not coming from the muscle itself, but in fact from the dissimilar metals and the juiciness of the muscle. So he basically takes two dissimilar metals like zinc and turns out turns out carbon can be one as well, even though we don't necessarily think of carbon as a metal. But you can take like zinc and carbon and separate them and put basically something that's not exactly pH 0 or excuse me, pH 7. Okay, something that has free charges that are free to move around it. So an acid or a base, or just water with some minerals in it that are free to break up. That kind of stuff always works. And you could make a what he called a pile. So what ultimately a battery is you can take a piece of copper, say, let's say a penny. Pennies aren't really copper, they're just coated in copper, but coated in copper is good enough. And you just take, and let's say we solder a wire to the back of that copper penny. Soldering just means melt metal that you can melt really easily, lead, which is obviously really good for us to breathe the fumes of and all that good stuff. So we're going to take this basic lead metal and we're going to melt it between the copper wire and the copper battery, and that's going to act like a glue that glues the copper wire to the copper penny. And in fact, itself is metal, so it's not going to lose any electricity because it's all a big conductor. So we've got that. We lay that down flat. And then we take, say, a little piece of gauze and we dip the gauze in pickle juice, or we even wipe it with the juice of a banana or the juice of a orange or juice of a grape or a lemon or something like that. Something that has basically what we now know of as things that are sort of held together by ionic bonds. And you stick it in there, and we call that an electrolyte solution or electrolytic solution, which probably tells you could use Gatorade. Okay. Now, next to the copper with the gauze on top of it, we'll put a piece of aluminum, and that'll work just fine. Any other metal other than copper will work just fine. Now, maybe that piece of aluminum has a wire soldered to it as well. And then you connect those two wires to one side to the positive terminal of a voltmeter and one side to the negative terminal of a voltmeter. And what you end up getting is a voltage. And it might be a very small voltage. It might be like reading like 0.2 volts or something like that. But that's okay. That's a voltage. And what's cool is if you now take off that aluminum cap and stick another piece of aluminum instead, and then another piece of gauze that's moistened, and then put the original piece of aluminum back on. Now, instead of 0.2 volts, it'll read 0.4 volts. And if you take that topping off again, put some gauze there, put another aluminum, and then another copper, and then another piece of gauze, and then the original aluminum back, then it'll read like 0.6 volts. So you can keep pile them up that way, and the higher you pile them, the higher the voltage will be. So that's why they are often called piles. They called this the electromotive force. And he published his paper in 1800, whereas Galvani published his in 1780. But the big deal is now, at that point in time, they have a source of electricity as opposed to just Leyden jars. So all that time before then, they were using something like a capacitance where you could fire all your electricity at once or nothing, right? So they were using things like the Wilmshurst machine or other devices where you just basically use friction to strip electrons off of some kind of metal or something, and then you collect them on something like a Leyden jar. And then whenever you wanted to do an experiment on electricity, you'd have to do that for each piece. And there were certain ways you could do it to get positive charge. There's a certain way you could do it for a negative charge, depending on what materials you were using. And you could do things, but like I said, you didn't have a source of them. Now, once Volta introduces his electric pile, he has a voltage source where he can continuously send out whatever this electromotive force is. Okay. Well, that electromotive force is what we now call voltage. It's also called tension. So you'll sometimes see something say high tension lines. High tension does not mean they're just pulled tight. They literally mean high electricity. Okay, so don't think, oh, this is a really tight line, that means it can hold me. No, that means that you could blow up if you touch that sucker. Okay, be like Jurassic Park when that kid was climbing down the fence. So that's the problem. Now, luckily, usually if you're actually separated and you were to jump up, say, and grab a hold of a power line, if you didn't touch another power line, if you didn't, sag the thing so much that you touch ground or a tree or something, in principle, you'd be fine. But there's a lot of ways that experiment can go really, really wrong. And there's really, other than just through local neighborhoods, those voltages are sometimes really high. Even local neighborhoods, they might be 800, 500 volts or something like that. If you get the ones along interstates, those suckers can be, 12,000 or 36,000 volts, something like that. And then the ones that you see going through fields on those, those things that look like humans with no heads, those are 500,000 to 1,000,000 volts. So the big thing with those, again, voltage by itself doesn't bother you. You can stand on 1,000,000 volts, no big deal. But if you reach over to 0 volts, then you're all of a sudden the conductor. And these are catastrophic incidents, like I said, like not just, oh, I got burnt or oh, I had a heart attack. Like, no, you explode. It's bad. So that's what we're talking about, electromotive force. Now, the other thing is what's actually happening when you apply electromotive force to a conductor, say. So I've already told you about how to do it. And if you want a little more mundane way of making a battery, you don't have to use copper pennies and aluminum, discs, which you can find a lot of those, by the way. Copper pennies are easy to find, of course, and aluminum discs you can find all over construction sites where they're cutting holes through various metal things and stuff like that. All you need is 2 different metals. But what I do when I teach it, like I used to, I'd still sometimes, but I haven't done it in a while, I do demonstrations for a local hands-on science museum in Elizabeth City, North Carolina, called Port Discover. And what we do there is I could make a battery for them, but I'll do it with like using a tomato or using an apple or using a banana. And actually all of those work. And then all I need is a piece of copper wire, which I go down to Home Depot and get one about that big around. And, you know, I need about 6 inches of it or 4 inches of it, something like that. And then I get a galvanized nail. So a galvanized nail is coated with a metal other than copper. And then of course, copper is copper. So that's two dissimilar metals. And I just jab the, let's say apple, jab the nail in one end of the apple, jab the copper wire in the other end of the apple. And then I can put it on a voltmeter and actually read it. And in fact, it usually reads on the order of a few tenths of a volt. And that's actually, for some diodes, that's actually high enough voltage to turn the diode on, so you actually get light. Sometimes you don't. Maybe it's a 0.7 voltage diode. In other words, it doesn't turn on until you get to 0.7 volts, in which case then I take another apple, do the same thing to, and then connect, say, the silver, or excuse me, say the copper end to the nail of the other one, and then the copper end of the next one to the nail of the third one. And then I connect it to a diode, and I got to do it in the right direction. If you do it one direction, you're going to get nothing. You do it in the other direction, then you'll get it lighten up. So that's a more mundane way to make electricity. And, you know, some of that stuff that the professor used to do on Gilligan's Island was actually somewhat legit. You can do it with coconut milk. So anyways, all you need is two dissimilar metals. And you've probably noticed this before. If you've ever had a weird feeling in your mouth, like when the dentist sticks something in your mouth that's metal, and it gets near like a filling, or if you actually have some aluminum foil you stick in your mouth and you'll feel, it feels like a magnetism or something pulling towards you. That's a galvanic process. It's the same thing that affects engines in water, because obviously you've got an engine that's made that has a prop, and that prop is usually stainless steel, say, and then the engine's like some crappy steel, or some parts are aluminum. Those are dissimilar metals. So what happens is one metal has more affinity for the electrons than the other metal. And in fact, some metals don't even hold it together good enough to stick together, like zinc. If you put it in a electrolytic solution, the zinc atoms will literally break off the zinc metal and go and like get attracted to, say, a carbon rod, or in the case of a boat engine, it would actually maybe stick to the steel on the propeller of the engine or something. So that's why sometimes you'll see people with boats will have little plates on the back of their transom, which is the part where the engine's sticking on, because basically you've got two dissimilar metals in there, and that slowly is eating away parts of your engine. But if you put another metal that's more likely to give up stuff, which is like zinc, you put that on there, then that thing will sacrifice itself and lose all the metal over time, and your engine will be left alone. So that's some of the neat stuff about it's really called electrolysis, but basically it's the galvanic process. Whenever you have a ionic solution, an electrolytic solution, separating two dissimilar metals, and you're going to have a voltage process go on, and that even creates a plating process too. So that's how you, for instance, gold plate for jewelry or stuff like that. So now that we've sort of discussed what the battery is, and I've shown you already what the battery looks like as a drawing in our sketches, it's just one single line that's short and then one long line with a gap between them. So it's like a capacitor, but one leg is shorter than the other. And sometimes they'll do 4 lines or even 6 lines. All you got to remember with that is the longer line on one end represents the positive side of the battery, and the shorter line on the other end represents the negative side of the battery. Now, when we go and connect a circuit, what happens? Well, let me show you that here. So I'm going to turn on my document cam, and I'm going to say, okay, we have a circuit, and obviously Mr. Younger did not focus that. Okay, so we have a circuit, and in our circuit we have a battery like this. And like I said, sometimes they have multiple plates to show a battery. That's a perfectly acceptable representation of a battery as well. Okay, again, the side with the shortest arm is the negative side, and the side with the longest side is the positive side, but they don't have to include the positive and negative because everybody understands that's what it's supposed to be. So there's your battery, and it might run off to, say, a light bulb. Okay, and what I mean by that is, if you look at a light bulb, I'm going to tilt this light bulb over a little bit away from us. So I'm looking a little bit at the bottom of the light bulb, like that, and then there's a little bit of metal around here, and then there's threads around here, So you can sort of see the threads going around. And then there's the casing. And then there's the bulb that we see from below, like that. And then here's the casing with the threads again, like this. So it turns out that this wire can just attach to the gold threaded part, okay? And this other wire can just attach to the ruddy looking, I shouldn't say ruddy, it's more of a gray, dark gray looking metal in the very center of that. That's where the electrodes are on a actual light bulb. You'll see in there, there's like a glassy or plastic type material between the gold band that's got the threads on it and the little nipple that sticks out in the bottom. There's a, like I said, like glass or something like that that does not look like a conductor. It definitely looks more like plastic or something. That's actually separating the two voltages from touching, or the two voltage terminals, if you will, from touching. So this, if you open this light bulb up, what you'd see is one end of this wire that seems to be coiled up like that. One end would be soldered to the gold threaded part, and the other end would be soldered to this part on the bottom. And in fact, if you were to take a soldering iron to that bottom, you'd see that that metal at the bottom is actually lead and melts quite readily for that purpose. Okay, so that would be where the other wire goes. And now this wire would come down and run back in to the back side of the battery. Okay, so with an actual battery, more or less what it would look like is this. We're going to have this little nipple on top, that's the positive end. And then we're going to have this right here is an insulator. And then inside of here is basically a zinc cup. So this thing right here, this inner part that I'm drawing that's just inside the insulator, that's a zinc cup. Okay, and in fact, it forms the bottom, which includes like a little dimple in the bottom, right? Now inside of this, I told you it can be two dissimilar metals, but one of them can actually be carbon. Well, what you'll see here is a black carbon rod. Simpsons of the fans will know that, in fact, a black carbon rod won Employee of the Month before Homer Simpson did. So, so this is a black carbon rod, and this actually makes the positive terminal. And basically, like I said, it's connected to the metal on top. That's the positive terminal. And all this stuff is separated like an insulator. It's only that part that's really conductor, and only the bottom that's really conductor. And inside of here is sort of a, well, they're alkaline batteries. So instead of it being an acidic paste, there's actually an alkaline paste. Remember, alkaline means basic. So alkaline paste is in there. And that's all you need. And when you have that, in fact, they found out that when you do this with the right configurations, then this will come out to be about 1.73 volts. And this will be, of course, 0 volts. That's normally what we measure it with respect to. And that voltage difference is good enough that when it actually draws a current, it won't sink below 1.5. So that's why they always make it about 1.73, 1.78, something like that. So over time, it's going to actually shrink. This voltage here is going to decrease over time. And what's happening is slowly all this zinc that's on this cup, parts are breaking loose and falling into this paste and just sitting there and making the paste more positive. And then the carbon rod being willing to accept electrons is going to take them and become more positive. Okay. Or another way of looking at it is a carbon rod can actually lose some of its electrons and release them to the paste and become more positive. Then when I connect it with a wire like I did here, then that's going to make this reach the exact same voltage. So when you look at the edge of a battery, you got to remember, hey, conductor is a source of constant voltage. It's a equal potential surface. So this whole wire all the way up to where it touches the light bulb is all basically at the same voltage. Now, in reality, this battery is establishing an electric field that is actually probably decreasing a little bit over this distance, but this resistance of this wire is so small compared to the resistance of the tungsten in that light bulb that you might as well say, if this is a 12-volt battery, then this would be 12 volts right here. And then again, there's going to be a potential difference from here to here. That's going to compel what we're pretending to be positive charges moving around this way. But again, this resistance is so low compared to that of, say, the tungsten filament, that this will be 0 volts, and so will this. Okay, but in reality, it's probably 0.001 volts, and this will be 0 volts. So that's what happens when you connect a circuit. We've sort of went over this already, but we didn't connect a light bulb. We just connected a capacitor. Now, this stuff, this charge is running around, is called the current. And we use the symbol I for it. And in principle, if you looked at a chunk of wire like this, and you took a given cross section right here, say cross section area A, if you counted all the charges going through this delta Q over that whole surface in a time interval delta T, then the average current would be delta Q over delta T. And the instantaneous current, of course, would be taking the limit of this as delta T approach 0 of delta Q over delta T, and that's, of course, dQ over dt. Okay. From that, we can see that the units of current should be equal to 1 coulomb over 1 second. Whoa. I ran out of my black pens, so I'll say 1 second and just scribble through that. My black erasable pens ran out, but this is actually defined to be 1 amp. Okay, named after I got by the last name of Ampere. Okay, so that's the current, and what we think of in circuits, as you know, you've probably already learned in lab or you've heard me talk about before, but it's exact analogy to talk about voltage as if it's a potential energy or a height, right? Because what we found out when we actually solved for voltage is V equals the negative integral of E dot dl, and it would have been the negative integral of F dot dl if it was just energy. But what we did was we divided the force by the charge to give the electric field. So it's actually the potential energy per unit charge. That's why it acts exactly the same. So what you might want to do is think of that circuit that we just drew. I'm going to think of it this way. This is this wire right here. Okay. And this too is this wire right here. And now I'm going to hang a corner, and that's that wire right there. So this is, let's say this point right here is A. This point right here is B. This point right here is C. And this point right here is D. And this point right here is E. And this point right here is F. So what I've got here is F, E, D, and they're all laying on the same surface as is C. Okay. Now, what we normally represent a light bulb or a motor or anything as is a load, and that load is given the symbol this. That's the sign for a resistor. But it can be used for anything. So this is a resistor. Now on the other side, we have, there's the low end of the battery. There's one of the long legs of the battery. There's another short leg. There's another long leg. There's another short leg. There's another long leg. Okay, so there's our battery. Now notice our battery has brought us up to an entirely different spot, that spot A, and I've actually walked up the hill. And then I'm going to take this corner right here by going back into the page, And then I'm going to take that corner right there and go to the left until I get right about here. And now I'm going to represent this like that. That's not that great, but I think you can see this is all one surface. Of one height. Like that, okay? And then that's a whole different surface, sort of like a bunk bed. So what you want to think of is the voltage is like the height, and then the current going through it is like the flow of water through a pipe. So we've got this flow of positive particles coming in here. They're not slowing down or speeding up along here because these are all the same height. But when it gets here, this motor, if you will, lifts it up. And now they're at a high height. And in fact, you realize that the pipe, in order for the water to go from here to here, the pipe has to slip down just a little bit, just like the pipe had to lower a little bit from C to F. But it's very small compared to the big step it takes along the resistor. So it gets along here, 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 and then it gets here, and then it goes down, 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 down. But notice it's a closed pipe, so none of the charge is lost. So every bit of charge that comes out of here is returned to it. That's just conservation of charge. So if you took, say, the current going through this little imaginary disk that the wire penetrates at any second, that would be exactly the same as the current flowing through this little disk at any second. So that really is sort of the way we like to look at our circuits, as if there's sort of this potential energy change, but really the height, instead of being 12 meters, is 12 volts. And right here it's essentially 12 volts, and in reality it's probably 11.999 because the wire has some resistance, and resistance, remember, acts like sort of the steepness of the setup. So the steeper down it is, the higher the resistance, and the steeper up it is, the more voltage the battery has. So any questions on that? So that's kind of a intro, if you will, to basic consideration of circuit issues. What we want to do is sort of get you familiar with that by making some sense out of, I'm trying to get something open up here. Sorry about that. By making some sense out of what these equations mean and stuff like that. So first off, what I want you to think about is, well, let's say a car engine. So this will be example one. A car battery might deliver 400 amps. And if you actually are driving a diesel, you might even look more like the 700, 800, 900 amps. For a time of 2.00 seconds. How, I don't know why I wrote HAW anyways. How much charge leaves the battery? And I'm putting that in quotation mark because there's a little bit of argument. Not necessarily every coulomb of charge that moves really comes from going literally through the terminal of the battery, but rather partly due to just the electric field establishing a direction for the charges that are already in the wire to go. So that's why I put that in there. How much charge leaves the battery in that time? So that's going to be A, and then B, how many electrons is that? Okay, so what we know is I is delta Q over delta T for average, right? So we could say that delta Q is equal to I times delta T. Well, I is 400.0 amps, and T is 2.00 seconds. Remember, our amp is defined as a coulomb per second. So we can automatically get for part A that this is 800 or 8.00 times 10 to the 2 coulombs. Okay, I did it that way because the 2 seconds limited me to 3 sig figs. So that's really the only way I can do it without putting a little dot on the end. All right, so that's the charge went through. Now part B, they want to know how many electrons is that? Well, number of E minuses is equal to delta Q over the charge of the electron, which is given that symbol E. So that's 8.00 times 10 to the 2 coulombs divided by 1.602 times 10 to the negative 19th coulombs per electron. So I can do 800 or 8 e to the 2 divided by 1.602 e to the negative 19th. And that gives me 4.993 times 10 to the 21. So that's 4.99 times 10 to the 21 E minuses. Any questions on that? Hopefully y'all didn't hear all that. I heard my dog making a mess over there. So I hollered for my daughter to ask her to check it out. So any questions on that? That's pretty straightforward, right? Simple stuff. Okay. Another thing you might want to, and your book talks about this, by the way, I want you to get some things straight about dealing with circuits. And this is something you would normally learn in a face-to-face lab because you do a lot of experiments with circuits in this course. So let's just take as example 2, how to connect things. Okay, so what I'm going to draw is I'm going to draw a multimeter. Yeah, I think Sean took care of it though. A multimeter has a knob on it, and it normally has a couple red, and then it has a black, and then it has a red again. And this red one, on the other hand, this red one's usually V and omega. So it's a little V and then a large Greek omega. And these are amps, and this is called the COM. This one in the middle is called the COM. That's the way a multimeter works. So you've got usually 1 or 2 red holes over here for different settings of ampere. So let me put it like this. And this is called the COM, and this is called V omega, which I'll write up here like that. And then you've got all these different settings around here. You want to make the setting set either to voltage or amperage. And that's what makes it a multimeter, because you can measure voltage, you can measure ohms, you can measure amps, you can measure connectivity. Some of them even do capacitance and inductance, all sorts of stuff. So that's what makes it a multimeter. If you wanted, for instance, to connect a light bulb, you could see already from the diagram I did before that you have to have a continuous path for the little charges to go through, all the way from the positive part completely through the little filament there, and then out the negative part, and then all the way back to the negative part of the battery. So if we were doing this one, we would connect this positive part to, and light bulbs don't matter which direction, so you can connect it to the gold part or to the little part on the other on the bottom. And then whatever one you chose, you do the other one and connect it to the bottom of this battery. So that's something to know. Now we've seen how we connect the batteries, but how do you connect these multimeters? Well, here's the deal. If you take this as your battery and you want to measure amperage, what you want to do is go into the voltage side, or into the excuse me, amperage side. So I got to turn the meter upside down to see this. So that's one of the voltage things. And then this is the COM. And this is the V omega. So this is the black one. I don't know why I'm writing it backwards, but I'm trying to, for, you know, I guess for consistency with this being drawn upside down. Okay. Now I want this set to amps. So I got to make sure the setting on the meters to amps, that's critical. And I'll read a certain number of amps. Okay. And then out of this common, it's going to go like this, come back up and go to our resistor like that. So what I'm trying to show you is that to connect an ammeter, in other words, a voltmeter measuring amperage, you have to break the circuit and you run the positive side into the red wires, into the red holes. Which one depends on how large the amperage you're doing, but you always start at the largest just to keep from burning up your meter, and then out of the common port. But it's what we call in series, because every electron that leaves, or every electron you're imagining leaving, has to go through that. So every electron goes around here. None of them get to bypass this ammeter. So that's in series. Now, when you want to do the voltage across the battery, well, what we do then is we take the same meter, and I'm going to say it's reading 10 volts. We make sure this knob is now set to volts, and we got the COM right here, that's the black part, and we got the V omega right here, that's the red part. What we're going to do with this is connect it here. And what we're going to do with this, I'm going to jump over that wire and connect it here. Okay. Notice that the high part of the voltage would be this side of the resistor, and the low part of the voltage should be this one. That's why I connected this one to the black common. And we still have these guys over here, but they're not being used this time. And this one to the V omega one, and you've got to have the knob set to voltage. Okay, so that's what that little thing means right there, is that's a knob set to voltage. Any questions on that? So parallel for the voltmeter. So the voltmeter's got to be in parallel, the ammeter's got to be in series, and you always have to have a continuous path that really completes the circuit. So it's got to go from the positive terminal of the battery through whatever devices you're running, and then back to the negative terminal. Any questions on that stuff? If you guys are former Navy or military or something, and y'all are actual electronic technicians, this part should be really easy for you. And that's good. I want y'all to do well, but I want you to help your classmates when lab time comes around, so you can make it easier for them as well. All right, so now that we've covered sort of how to set up circuits and stuff of that sort, now we're going to go on and talk about some of the laws that we use. And one of them, for instance, is Ohm's Law, which you should have already done in lab, I believe. So this is called Ohm's Law. And it's more about telling how things behave. And there's a lot of different ways to interpret it, but we normally just say V equals IR. And what we're saying is, if you make a plot of voltage versus resistance for a metal conductor, okay, it turns out that generally speaking, taking data along that will give you a straight line. Now, it's not exactly straight, but things that do give you a roughly straight line over a decent, you know, small but decent sized range of temperatures, those are called ohmic devices. So most metal resistors are that way. But in fact, if you actually change the temperature of this metal conductor, the resistance will change. In other words, the hotter it gets, the more resistive it'll be. But you can see from here and that equation that clearly the slope is the R. So that's basically telling you, hey, if I double the current, then I'm going to double the voltage across the device. If I triple the current, then I'm going to triple the voltage across the device. That's what Ohm's law tells you. But you can also treat it as Ohm's law tells us how metal conductors behave, at least over a pretty small range of temperatures, in that this R will be a constant. But hopefully, as you saw in lab, if you do that same thing for a light bulb, you'll notice that the light bulb, which is actually made to change resistance really quickly because it's made to change temperatures really quickly, that light bulb will do something like that. But in that sense, R is sort of like the instantaneous resistance. In other words, the slope at any one point can tell you how the circuit's behaving at that particular point. So that's another way of looking at it as well. But in general, whenever you have something that has a resistive part to it, in other words, something that's going to steal some of the energy away, the current doesn't change, but the voltage will, and the amount of change of that voltage will be given by V is equal to I going through it times whatever we represent its resistance as. Does that make sense? And the way current goes, by the way, is from high voltage to low voltage. So current, because we're talking about positive conventional current. Current flows from high V to low V. So that's why I was telling you in the previous diagram that you put the red side of the voltmeter, whether it be a voltmeter or ammeter, you put that to the higher voltage end. That way you don't get a negative. The good news is, even if you do put it backwards, it's okay, because you can still just take the same number but remove the negative and it'll be fine. Okay. So a way of looking at this statement is basically saying this is high voltage. And this is low voltage, and current goes that way. Does that make sense? So here's an example. Let's say a toy uses, let's say, 150 milliamps of current from 2 stacked 1.50 volt batteries. What I mean by that is they're stacked like that, so that if you actually connect it to a voltmeter, it would read 3.0 volts. Okay. What is the toy's resistance? See, this is a big deal. This is actually a little motor that's running. Like, you can expect it to be a toy, maybe it's a toy truck or toy car or something like that. Well, according to Ohm's law, V is equal to I times R, so R should equal V over I. And what we get for that is R is equal to 3.00 volts, because it's two AA batteries, which are essentially supposed to be 1.5 volts. And that's going to give you 3 volts. And that's divided by 150 milliamps. Well, when you divide a volt by a milliamp, you're actually getting kilo ohms for starters. So I could just put that M up top and make it a K. And then I'd have 3 divided by 150. But if I multiplied that by 100, it would be 300 divided by 150. So that's 2. So I just got to take 2 and divide it by 100, and I'd get 0.0200 kilovolts, which is also equal to 1, 2, 3, 20, or excuse me, I said it in volts, kilo ohms. I really missed my erasing pen. So notice that's kilo ohms, but if I want to get rid of that 10 to the 3, all I have to do is divide it by 10 to the 3 and multiply this by 10 to the 3. So it's 1, 2, 3. That'd be 20.0 ohms. Okay. Any questions on that? Pretty easy stuff, right? This makes sense? All right. How much current would be drawn if the batteries were weak and only had voltages of, let's say, 1.30 volts? I don't want to do that yet. Oh, I did say, okay, yeah, I can put the question mark there now. I forgot I'd written what current would be drawn. So this is the same sort of problem, but now we're solving for current, and V equals IR tells us that I is actually equal to V over R. So the V in this case is going to be 1.3 volts plus 1.3 volts. That's 2.60 volts. And the resistance we can assume would be the same resistance, or we're going to try to assume would be the same resistance we had before, and that's going to be 20.0 ohms. Did anybody verify my math on that? Because you know how I am with my math. I'll do that real quick. Yep, I got 20. That's cool. All right, so I'm going to say 2.6 divided by 20. And that gives me 130 times 10 to the negative 3. And this is amps, of course. Well, that's the same thing as I is equal to 130 milliamps. And I should put a dot there just to represent that all 3 sig figs are relevant there. This stuff's a lot easier than what we've been doing, right? No questions on that? No questions? Is everybody even there? All right, now that go ahead.
Said I'm here.
Yeah, glad somebody is. Just particularly quiet because it's been a rough weekend, right? All right, I'm gonna stop using this black pen. It's aggravating me. This is actually my favorite type of pen. I actually buy them by the case, but there's ones that erase, make life a lot easier. So here's example 4. Actually, no, I'm not even doing example 4 yet. Yep, here I go again, pseudo erasing. So what I want to do now is talk to you a little bit about what resistance is. So let me stop using this pen that I can't erase with and use a pen that I can erase with. Well, resistance, if you think about it, you can probably figure out how resistance should be related to geometry. So your book opens up the chapter with like 4 different wires. So it says, here's one with an itty bitty cross sectional area and a really long length. Here's one with an itty bitty cross sectional area and a really short length. Here's one with a huge cross sectional area and a really, really long length. And here's one with a huge cross sectional area and a really, really short length. Okay. You can imagine as an analogy that we're trying to push people through these tunnels are, and let's say the tunnels are about 4 foot tall. Okay, so that the height really matters too. Okay, so the cross-sectional area really matters. Which one of these tunnels takes the least amount of time to get through? A, B, C, or D? Remember, this cross-sectional area seems weird because it's round, but the more agile and younger people could actually walk sort of on the walls, and they're short and stuff like that. So it actually does matter that the cross-sectional area is a little bit bigger. So if you're trying to evacuate people from a building, and the people range from walking toddlers to elderly, which one of these will allow 100 people to go through fastest? D, yes.
D.
And it turns out that's the exact same thing as what would happen with the least resistance. So I either make an analogy of like getting people out of through a tunnel out of a building, or I'll say like it's a slam dance or something like that. And how easy would it be to go through all this? The big deal here is that yes, the cross-sectional area being bigger and bigger and bigger allows more people per unit time, and the shorter distance, of course, allows more people per unit time. So in fact, you can now figure out that this is the length L, and that's the cross-sectional area. So the formula for resistance is obviously proportional to the length, because the longer the tunnel is, the more time it'll take. And inversely proportional to A, that means thumbs up, thumbs down. So high area means small time, or large time means small area. Now, the last thing that matters is what's the metal. We know, for instance, that we use a lot of copper, so that must be pretty good. And we know that we don't use steel very often, so that must be kind of crappy. So we represent that by the resistivity, which is a property of a material. Okay, so you can look, for instance, in your book, and they have an actual table of resistivities and coefficients of resistivity, temperature coefficients of resistivity. And you see, for instance, like rho for silver, which is Ag, rho for silver is 1.59 times 10 to the negative 8th. And the units, of course, turn out to be ohms times meters. Well, that's a really great figure, because when we look at the one for copper, we get 1.68 times 10 to the negative 8th ohm meters. Now, why do you think we're using so much more copper? Why aren't we using silver?
Availability.
Yeah, and the fact that it's not that available means it's expensive as crap too. So yeah, and if you look at gold, don't let people fool you with that one. Gold is actually not that good of a conductor. It's like 2.44. Yeah, 2.44 times 10 to the negative 8th ohm meters. Aluminum, on the other hand, is not bad. It's worse than gold, but it's still not that bad. And in fact, they could use a lot of aluminum wire to go large distances. One, because it's a lot lighter, and two, it's a little cheaper than copper. So aluminum is 2.65 times 10 to the negative 8th ohm meters. Okay. So with that in mind, you can readily calculate the resistance of a piece of wire. So let's do example 4. Let's say 200.0 kilometers of wire of, let's say, 1 inch diameter, and I'll say that's 1.00 inch. Can be made of copper or aluminum. A, what are each wire's resistance? And B, weight. Okay, so that's a straightforward enough problem. Of course, I need to know the density of aluminum, and I need to know the density of copper. So let me Google that real quick. Or if anybody could Google that, that'd be great. I think copper is 2.66. But anyways, let's start with part A. And if someone would Google that for me, that'd be awesome. I want to say part A. Let's say the resistance of the copper is equal to 1.68 times 10 to the negative 8th ohm meters times 200 times 10 to the 3rd meters. And then I happen to know that 1 inch is 2.54 centimeters. And since that's 2.54 centimeters, I know that the, of course, resistance is half of that, which would be 1.27. So I'm going to say pi times 1.27 times 10 to the negative 2 meters squared. That's the area, right? So let's do that. I'm going to take 1.68. I'm going to show you my calculator too, so y'all can see if I make a careless mistake. 1.68 e to the negative 8 times 200 e to the 3 divided by, here's where I'm going to use parentheses, 3.14159. That's more than enough, times 0.0127 times 0.0127. That gives me 6.631 ohms. That's really small. And that's carrying 1 extra sig fig. Now let's do the one for aluminum. The only difference would be it's 2.65 times 10 to the negative 8 ohm meters. Everything else will be the same. So I'm going to take this number and divide it by 1.68 e to the negative 8. And then I'm going to multiply it by 2.65 e to the negative 8, because that's the easier way of doing it. And that gives me 10.459 ohms. So that's what, 50%? That's a 10, not a 16, by the way. That's about 50% more resistance. So not horrible, but 50% is quite a bit different. So did anybody bother? Oh yeah, 8.96 times 10 to the, or excuse me, 8.96 over 10 to the third. I mean, over centimeters cubed. So the volume of the wire is equal to pi r squared L, right? So the volume is going to be 3.14159 times 0.0127 squared times 200 e to the third. That gives me 101.34 cubic meters, which is a buttload. Okay. And 8.96. I'll write this over here. Rho copper, 8.96 grams per cubic centimeter. That also happens to be 8,960 kilograms per cubic meter. So I'll multiply 8960. Dang it. 8960 times 101.34. So I'm going to say M copper is 908 times 10 to the third kilograms. M aluminum, and I said I thought aluminum was 2.66. Let me double check that, or did somebody find that that was the case? Yep, 2.66. What's that now?
Oh, you said you were looking for density of aluminum?
Yeah, I got 2.66. And I just
it's in kilograms per cubic meter, but
it's going to be 2,770 or 660 or something like that.
2,705.
Okay, 2,705. All right, so I'm going to stake 2,705. And I'm going to multiply that by 101.34. And that's going to give me about 274 times 10 to the third kilograms. So you can see 274, that's less than a third of the weight of copper. Not to mention that, you know, aluminum is a little bit more inexpensive than copper. So yeah, you can definitely see that there's an advantage to using aluminum over copper. My dad worked for the power company and for 30 some years or whatever. He tells me about all these wires being made out of aluminum and stuff like that. He tells me, you know, that the power lines going overhead, he told me they're 13.6, which means 13,600 volts and all that kind of stuff. So it's kind of neat hearing from them exactly how they do it. But yeah, it's really various stages that are the standard, and there's certain parts of the pole that are for certain things, and you're not allowed to have the wires but for so close to each other. And sometimes I'll see like construction workers take a 2x4 and prop up a wire so that a large truck can get under it. And there was one, for instance, on Battlefield Boulevard for a long time, about this time last year, and they left it up there for several weeks. And all I could think was, when it was raining, if someone walked by and were to touch that 2x4 with it soaking wet like that, it probably would have zapped them pretty darn good, because those are down battlefields probably 13,600. But you can prop it up like that, and since wood's not that great of a conductor, if the voltage isn't too high, then the wood, you know, won't conduct electricity to harm you. But when it gets wet and you touch it, then it's a really conductive piece of material, and all bets are off. So, any questions on what we've done so far? All right, so there turns out to be another parameter of resistance that can screw things up. I think you can see pretty much how these things go. They're not that difficult of problems, but you can imagine more severe things where they can make you, you know, do a lot of more complicated calculations and stuff like that. So here's example 5. And I'm going to start off by giving you a little intro. So you might think, that resistance and temperature are related, meaning the higher the temperature, the higher the resistance. And in fact, that is the case. The higher the temperature, the higher the resistance. And that's basically because the what causes current to flow is the same thing that causes heat to flow. That's little loose electrons in a conductor are free to move about the conductor, but they move through the conductor, not necessarily hugely fast either, but they do move through the conductor, and the atoms that they used to be attached to are vibrating all over the place. So those atoms will be hit by the electrons every now and again, and the electron loses some energy. If you actually raise the temperature of that metal, not only do the electrons speed up, but the atoms speed up as well. So there'll be a lot more collisions and a lot more resistance to the flow of heat, or resistance, or excuse me, resistance to the flow of current, which is charges flowing. So if you want to actually think about what the resistance is or how the resistance changes, what you can say is you can imagine that the change in resistance per unit temperature is roughly equal to a constant. And let's call that constant, unfortunately, alpha. Okay, that seems to make some sense. And in fact, it is roughly a constant for a given temperature range. Once you get outside that temperature range, it's an entirely different constant and stuff like that. We can talk about resistance, but we might want to talk about something that doesn't have the complications of the material changing. So if you do that, then you can say that the change in resistivity, which we found was ohm meters, per unit temperature is on the order of alpha. And that's what we normally use, but you can use both equations. I should also mention that, by the way, this resistivity has something called conductivity. Okay, that's the conductivity, and that's measured in reciprocal ohm meters, of course. But anyways, that's another parameter we can use. In place of rho, we can replace it with 1 over sigma, and then sigma is the conductivity, not to be confused with the charge per unit area that we were working with before. So when I have this written this way, then I can say, okay, well, delta always means final minus initial. So I'm going to say rho minus rho 0 over T minus T0 is equal to alpha. Okay, I'm going to say that's just set to a constant. Now I can multiply both sides by T over T0, and I get rho minus rho 0 is equal to alpha times T minus T0. And this quantity is called the temperature coefficient of resistivity. Temp coefficient of resistivity. Okay, and then finally, the equation that your book gives you is rho is equal to rho 0 times 1 plus alpha T minus T0. Okay, that, I'm pretty sure that's what I ultimately had. Yes. Okay, so that is ultimately the expression we wish to use. And with that in mind, now we can do calculations of how the temperature changes. So for instance, we can look on that same table, and that table, by the way, was on page, let me look that up real quick. It was on page 658. Wow. I think I just literally had a stroke. So page 658 is the table, and that table gives us stuff like the resistivities, which I told you before, but the temperature coefficient of resistivity, alpha for, let's say, platinum, is actually equal to 10.6 times 10 to the negative 8. That's the, I just wrote down the resistivity instead of this. temperature coefficient. Sorry about that. So alpha, the temperature coefficient for this is 0.003927. 0.003927, and that's actually in reciprocal Celsius degrees. Okay, and we put the Celsius, the degree symbol after the Celsius because it's supposed to be multiplied by a subtraction of temperatures. We'll learn that more in thermodynamics, but when you subtract two temperatures, we sometimes keep that as a separate unit by calling it Celsius degrees instead of degrees Celsius, whereas each one of these has, 271 degrees Celsius minus 270 degrees Celsius or something like that. Okay. So our examples now are going to be us making use of that. So let's say if the resistivity of platinum is, actually I should have kept that number because I need it now. Resistivity of platinum 10.6 times 10 to the negative 8. At 20 degrees Celsius, what is its resistivity at, let's say, 40.0 degrees Celsius, and I'll call this 20.0 just to make sure. So that's our example. Well, what we know is the initial resistivity is rho 0, so I'm going to calculate just simply the new resistivity. This is going to be 10.6 times 10 to the negative 8 ohm meters times 1 plus 0.003927 reciprocal degrees or Celsius degrees times, now I'm going to do final temperature, which is 40.0 degrees Celsius minus 20.0 degrees Celsius. This is the part when we do this subtraction, the resulting unit, we sort of pretend like that's something different, that it's Celsius degrees. And that just is another helper for us to remember what we're doing. So that's clearly 20.0 when you do that tough subtraction there. So I'm going to say 20 times 0.003927, and that gives me 78.54 times 10 to the negative third. Okay, now I'm going to add that to 1, which is obviously not that big. So I get 1.07854, and now I'm going to multiply that by 10.6 times e to the negative 8. And that gives me now 114.33 times 10 to the negative 9th ohm meters. Now, that's not necessarily that helpful. Let's put it back in the power of 10 to the negative 8, which we had 10.6 before. If I multiply this by 10, that becomes 10 to the negative 9 times 10 to the positive 1, 9, negative 9 plus 1 would be negative 8. But by multiplying it by 10, I got to divide this by 10. So this is going to be just 11.43 times 10 to the negative 8 ohm meters. So you can see even over a swing of 10 Celsius degrees, which is a pretty good swing, remember, that's like what, 18 degrees Fahrenheit change. It doesn't change the resistivity that much, but it does change it. And that's in fact what we use to find temperature with electronic devices. Basically, we'll have a tungsten filament, or excuse me, a platinum filament or something, and we'll have a circuit set up that basically tests its resistance and then uses a formula to take that resistance, resistivity, say, or resistance, either one, and it will spit out the actual temperature. And all it's doing is using something like this. And the reason we use platinum is platinum doesn't oxidize too easily. It's not going to just rust and all that stuff, and it can handle a large range of temperatures before melting and stuff like that. So they'll actually make a device like this, and that can be used to measure temperatures of liquids. Say you just submerge it in the liquid, it reaches equilibrium with it, and then you test the resistivity, and it tells you, or it figures out what the resistivity is, and then computes the temperature from this formula. So that's another thing you can do with that. Any questions on that? Okay, so that's the first maybe 5 sections of chapter 25. So we've got about 3 or 4 more minutes left in class. I think actually it's about 6:03. So we actually got about 7 more minutes left in class. Does anybody have any questions on this material? I'm trying to remember if there's anything else that I want to try to fit in today. I don't think anything else falls out. I guess I could do power. Yeah, so let me do power. So the last thing we'll talk, that'll be section 25.5 too. If you remember correctly, we had a formula earlier that we used, and that was delta U equals Q delta V. Remember, that was the origins of the electron volt, for instance. 1 electron volt is equal to 1 times 10 to the negative 16th coulombs times 1.00 volts, which equals 1.602 times 10 to the negative 19th joules. So you can see that looks like a charge times a voltage. That's what that is. So if we make this into differential form, we call this Q dV, right? So if we would like to calculate, for instance, well, we also could make this, instead of that, we could say that's going to be V dQ. Either way works. Like you could consider a change in the current and the charge, or a change in the voltage. I'm going to choose to use this way. And when I do that, I can say, okay, well, work is equal to du over dt. So using this form, I would say that's equal to V dQ over dt, but dQ over dt is I, so it's IV. And of course, I said work, stupid me. That was supposed to be power. Power is equal to dW dt, which is the same thing as du dt. So that's a famous formula as well. It's just about as famous as Ohm's law, and it's P equals IV. Of course, now you can use Ohm's law. If you don't know the voltage, you can replace the voltage with IR, and you get I squared R. And if you instead don't know the current, you could replace the current with V over R. So let's see, current with V over R. Yes, you could replace the current with V over R, and that'd be V squared over R. So there's 3 different versions of power. And this one right here, this particular version, is particularly helpful for us, and it explains to us, for instance, why we use AC, or a good reason why we use AC. In fact, in the early 1900s, there was a big battle over electrifying America, and it was going on in New York City. And there was 2 big name people, one of which you might know from the light bulb. Anybody?
Edison.
There you go, Edison. And the other one you might know from some very rare TVs, but I happen to have one in my living room. Also various other electronic devices that start with W. Anybody? That one's, go ahead.
What?
Oh, no, it's a good one, but he was over in Great Britain. It's actually Westinghouse. So Westinghouse and Edison were both very much entrepreneurs. Edison was somewhat of a scientist as well, obviously, but they were basically trying to get the contract to electrify America, and they were slowly doing bits and bits and stuff like that. Well, Edison was using DC. In fact, he's pretty well established that he didn't really understand AC that well. Though he probably understood it better than most people that understand AC and DC. Westinghouse, however, was pushing somewhat for AC, And that was mainly as a result of the guy by the name of Tesla. So Tesla comes across from the former Soviet bloc area. Actually, it's dang it, where is Tesla from? Yugoslavia area, basically. I can't remember the country right now. Maybe someone does. I feel bad for flopping on this. I wasn't going to talk about this tonight because I wasn't doing this one. But anyways, Tesla comes from that region of what was very close to the Soviet bloc and stuff like that. He comes here, and basically he had met one of Edison's friends and engineers, and gave him a letter and said, "Hey, go see Edison. He can help you get a job." So the guy comes all the way to America. He waits all day for an appointment with Edison. Edison's kind of Croatia. Thank you. I think he is Croat. Yeah. So anyways, Edison more or less blows him off the whole day. And then finally, at the end of the day, he finally gets to see Edison. And he says, "I have a letter from such and such." And he hands him the letter. And the letter says, "I've met two brilliant people in my life, you and this guy." So that's his note of introduction to Tesla. He said, "Well, such and such thinks you're smart enough, but that remains to be seen. Here, if you go out and fix the power outage in this thing, I'll give you a job." He's like, "Okay." So Tesla just got here into the States, runs to a power plant facility that Edison's made, and starts fixing it, and fixes it promptly. So Edison turns out to be a brilliant. Edison sees that this guy's brilliant, and of course hires him, and then proceeds to steal all his patents. And then Westinghouse sees him mistreated and wants to mistreat him himself, I think, and steals all his other patents, basically leaving poor Tesla destitute. But Tesla was a brilliant man. He had, I wouldn't say his life was miserable. I think he actually enjoyed his life till the day he died, living in a hotel, leaving his windows open 24/7 so he could play with the pigeons or whatever. But he's the reason we have 60 hertz, and he's the reason we have AC power. And during that horrible battle, basically Edison staged, I think it was in Minnesota or Michigan, he staged using AC voltage and exploded. I tell you, I kid you not, he exploded or blew up a elephant to show people the horrors of AC, which you can do with DC as well. And he knew that during good and well, so just being a punk. But anyways, that's some of the horrible things that went on at that time. But still, it's a friggin' awesome story. I definitely recommend you try to read some histories of this. Sadly, Tesla's filled with pseudoscience. So a lot of people that like Tesla believe that he had magical powers. And they'll even say, I remember reading Cheney's description of it. He said, even though Tesla was not convinced of his magical powers, we all knew he had them. Tesla did not think he had magical powers, trust me. But anyways, so that's the reason, one reason we use AC is this thing right here tells us if we're going to push power across 14 miles, there's a resistance that's going to happen no matter what. Once you choose aluminum wire or copper wire, that resistance is fixed based on the distance you got to go and the wire you use. And guess what? The amount of current that goes through that wire, if you double it, if you go from say 100 amps to 200 amps, then you take the power that's being dissipated in heat, and that actually quadruples. So that's a horrible thing to happen, right? So what they do is they actually use a step up transformer, and we use roughly, it's pretty much 125 voltage, but we use it in triphasic. So if you line it up just right, you can get double it. But that's what we send out, and each house gets about a 200 amp service. So depending on how many neighborhoods you're going to do, that's going to fix this current to a certain amount. But if you take that current and you change the voltage of it from 200 volts to say 1,000,000 volts, then you decrease the current by the exact same factor that you increase the voltage. Therefore, you reduce power loss. So I'll leave it at that. It's time to go. You guys are free to go. See if Cadmium, if you're in here, I just sent you an email. I'm going to fix that tonight. And I think that was it. But the only person that had it sent me anything from this class. So I will have that up tonight, and I'm going to give you the whole week until Monday of next week. Actually, I'll give you till Wednesday of next week because we got a test due Monday. Anybody else have any questions? Or anybody have any questions, period?
I think we're good, Professor.
All right. Thank you. I appreciate you coming.
Have a good night, Professor.
You too. I will be at school tomorrow if anybody needs office hours, needs to see me or whatever. How's it going, Georgie? I don't think she's there. Good night.